the amino acid oxidase O2 involved a reaction. Okay. Okay. So this is the O2 involved reaction, but for conversion of FMNH2 to FMN O2 involved the reaction O2 accepting 2 electrons become H2O2. Okay, so this is the amino acid oxidase enzyme. The amino acid oxidase enzyme O2 involved, okay, but released as H2O, and the amino acid become keto acid, and NH2 released as NH4. Okay, so and fat to fat H2. Okay, fat to fat H2. So in this reaction, O to H2O. Okay, so in this reaction, the electron acceptor, electron accepting hydrogen from fat H2. So converted, oxidized by fat H2, oxidized by oxygen. So oxygen accepting electron. So it is oxidase enzyme.
الانزيم هذا دي امينو اسيد اوكسيديز ال بس امينو اسيد
No. L-amino acid in proteins only. Only proteins in protein. The structure of amino acid in proteins, all of them are L-amino acid. But the amino acid, there is D, free amino acid, and form of D, there is, but free, not in complex with. So all structural proteins consisting from alpha L amino acid. Okay. So oxidase enzymes. So electron acceptor. So 2 electrons accepted by oxygen converted to H2O2. Electron acceptor. Oxygen. So what are the differences between oxygenases? Fixation of oxygenases, and oxidases. The electron acceptor is oxygen. Okay. The last one it is peroxidase enzymes. Peroxidase enzymes. Peroxidase enzyme. And peroxidase enzyme is classified into hydroperoxidase classified into peroxidases and catalase enzyme. Peroxidase enzyme, the electron acceptor is other compound other than H2. So peroxidase enzyme catalyze the interaction between the electron acceptor, electron donor, as for example glutathione, with H2O2. So electron acceptor is hydrogen peroxide. The electron donor is compound other than hydrogen peroxide. Okay, converted to H2O plus oxygen and GSSG, 2 molecules. Okay. The catalase enzyme, the electron acceptor is H2O2, and electron donor is H2O2. So one of them works as acceptor, another as donor of electron. Catalase enzyme. Catalase enzyme. H2O plus. Okay. So catalase enzyme catalyzing the interaction between two molecules of hydrogen peroxide. But peroxidase enzyme is catalyzing the interaction between hydrogen peroxide and other compound other than hydrogen peroxide. Okay, so electron acceptor is hydrogen peroxide, but electron donor is the other compound other than hydrogen peroxide. But in catalase enzyme, it is the interaction between two molecules of catalases. One of them will work as electron acceptor, the other will work as electron donor. So these are the classes of oxidoreductases enzymes in our biological system. So dehydrogenases, oxygenases, oxidases, and hydroperoxidases. Dehydrogenase is classified into aerobic dehydrogenase, anaerobic dehydrogenase, oxygenases to monooxygenases and dioxygenases, oxidases to L-amino acid, for example, L-oxidases and deoxidases, for example, L-amino acid oxidase, D-amino acid oxidase. In some classes, hydrogen peroxide is produced, as in case of L-amino acid oxidase, but in D-amino acid oxidase, no hydrogen peroxide produced. Hydroperoxidase is classified into catalase enzyme and peroxidase enzymes. Catalase enzymes highly present in peroxisome and lysosome. Peroxidase enzyme is also present. Therefore, we call them peroxisome. Peroxisome highly rich in lysosome, lytic enzymes, and peroxisome. Okay. Okay. So these are the enzymes involved in oxidation reduction reactions. Okay. The place of electron transport chain is the mitochondria. Yes? Mitochondria. The electron transport chain located in the inner side of mitochondria. This is the matrix. Where is the Krebs cycle relocated, occurring place, and the electron transport chain embedded the inner side of mitochondria. This is the outer side of mitochondria. This is the inner side of mitochondria. This is the interspace membrane. Okay. Some NADH produced in cytoplasm. Okay. We know that the substrates of electron transport chain is NADH and FADH2. When produced in mitochondria, so the substrates produced beside the complexes, near the complexes. But when the NADH produced in cytoplasm, the NADH must translocated from cytoplasm to mitochondria. There is no channels can lead to transportation of NADH. No, we have not. There is mechanism by which hydrogen of NADH translocated from cytoplasm to mitochondria. translocated from cytoplasm to mitochondria. So, mechanisms by which NADH translocated from cytoplasm to mitochondria. So, mechanisms are electron transportation from NADH to mitochondria. Number one is glycerol 3-phosphate pathway mechanism. Okay. So NADH is produced, for example, from glycolysis, which which occurring in cytoplasm. For example, glyceraldehyde phosphate to 1,3-bisphosphoglycerate. Glyceraldehyde 3-phosphate dehydrogenase. Yes? So produced from glycolysis. Must translocate to the cytoplasm, to the mitochondria. So glycerol 3-phosphate. That way. Mechanism. Number one. Dihydroxyacetone phosphate. CHOH. CO. CHO phosphate group. This is dihydroxyacetone phosphate. When accept 2 electrons, NAD, it's so 2 electrons will translocated from NADH to oxygen of dihydroxyacetone phosphate. So this compound will gain electrons. Reduce it to. So CHOH. Can see it is. And it's okay. COH. So this compound, oxygen, will gain 2 electrons. Reduce it to alcohol. OH. Yes? And CO phosphate group. H. Glycerol 3-phosphate. Glycerol 3-phosphate. Glycerol 3-phosphate can cross inner and outer mitochondrial membrane. And NAD will oxidize it to NADH will oxidize it to NAD. So 2 electrons of NADH translocated to or transferred to dihydroxyacetone phosphate. Dihydroxyacetone phosphate accepting electron becomes glycerol 3-phosphate. Glycerol 3-phosphate can cross outer and inner mitochondrial membrane to the mitochondria. Okay. COH, COH, H2, yes? CO phosphate group, H2. Okay. Glycerol 3-phosphate. Glycerol. So this enzyme, this reaction will catalyze it by glycerol 3-phosphate dehydrogenase, but cytoplasmic isomer. Cytoplasmic isomer. Okay. So there is cytoplasmic, there is mitochondrial. Mitochondrial. So there is two electrons here, two electrons will translocated from glycerol triphosphate to fat, become fat H2. So fat can accept two electrons, reduce it to fat H2. Okay, 2 dihydroxyacetone phosphate. Okay. So electron is transported from NADH to dihydroxyacetone phosphate, becomes glycerol triphosphate. So glycerol triphosphate is a carrier of electrons. When translocated to matrix, in matrix there is mitochondrial isomer of glycerol triphosphate dehydrogenase. Mitochondrial isomer will use fat as coenzyme, not NAD as coenzyme. And fat equal how many ATP? 1.5 ATP. NAD is 2.5 ATP. Transportation of electrons from NADH by glycerol triphosphate pathway led to losing of 1 ATP. Why? Because mitochondrial glycerol triphosphate dehydrogenase not using NAD as coenzyme but fat H2. Fat as coenzyme, not NAD. Therefore, will be losing in energy when the NAD electrons in NAD is transported by this pathway. Okay? There is also aspartate malate shuttle. Aspartate malate shuttle. Aspartate. So, second pathway by which electron is transported from cytoplasm to mitochondria. So, NAD or NADH cannot cross the inner and outer mitochondria. But the importance of NADH, it's electrons. We want electrons only, not NAD. Our interest is the electrons. So electrons transported to mitochondria, and it is good. Okay. Malate, aspartate, shuttle. Okay. This is the inner and outer mitochondrial membrane. There is NADH produced in cytoplasm. For example, glycerol triphosphate, glyceraldehyde triphosphate dehydrogenase in glycolysis. What produces NADH? Okay, NADH produced from, for example, glycolysis. Must transport electrons, two electrons, must transport to mitochondria. So NAD will donate electrons to oxaloacetate. Oxaloacetate COOH COCH2 COOH. This is oxaloacetate. Okay. So electrons will be transported from NADH to the oxaloacetate. oxaloacetate. When oxaloacetate reduced
ماليت
malate, COOH, reduced O, oxygen, this carbon reduced to alcohol. OH, yes, CH2, COOH. So this carbon is a carrier for 2 electrons. Malate, as we know in gluconeogenesis, can easily cross the mitochondrial membrane. Okay? So, to the mitochondria. Okay. So, COOH, COH, CH2, COOH. Yes, this is malate. Malate, oxaloacetate. So, malate, dehydrogenase. It is one of the interactions in Krebs cycle. So, NAD will gain electrons from malate. So 2 electrons will transport to NAD, and NAD become NAD H, okay, to malate, to oxaloacetate. H, CO, CH2, COOH. But oxaloacetate cannot cross the inner and outer mitochondrial membrane. Must transaminated by aspartate aminotransferase. So the oxaloacetate must be transaminated, and the transaminated oxaloacetate is the aspartate. Aspartate, yes. Aspartate aminotransferase. AST, aspartate aminotransferase. Aspartate aminotransferase أو transaminase مرة ثانية. نحتاج إلى B6 as coenzyme BLP bioredoxyl phosphate. So the oxaloacetate transaminated by glutamate. Yes, glutamate. This is the composition of glutamate. CNH2, CH2 multiplied by 2, COOH. This is glutamate. So glutamate become alpha ketoglutamate. Transamination. So transamination. Transferring of NH2 to oxaloacetate. So oxaloacetate become COOH, CNH2, CH2, COOH, aspartate can cross the mitochondrial membrane. Aspartate. This compound will become amino acid, become keto acid. COOH, CH2, COOH. This is alpha ketoglutarate. Translocated alpha ketoglutarate. Okay, so aspartate translocated, alpha ketoglutarate transport, glutamate also can cross glutamate, can cross outer mitochondrial membrane. aspartate.
حاول كذا.
The amino group will transfer from aspartate to alpha ketoglutarate. So alpha ketoglutarate become glutamate. Reversible reaction. This reaction is reversible. هذا الميكانيزم اللي نسموه فيه شنو؟
شتت.
ساعة لاندرو شو يسموا فيها؟
بيج بوك.
بيج بون ميكانيزم. اسبارتيت ماليت اسبارتيت ماليت اسبارتيت ماليت ساعة. Okay. So big bond. Okay. So this is the mechanism by which electron is transported from cytoplasm to mitochondria. So there is no mechanism by which NAD or NADH translocated, but NADH can be transported from cytoplasm to mitochondria. Okay. So two main mechanisms. Aspartate, transportation of electrons by malate aspartate shuttle, there is no loss in energy. Why? Because mitochondrial malate dehydrogenase also using NAD as coenzyme. Using NAD as coenzyme. So there is no loss of energy. But transportation by glycerol triphosphate, the mitochondrial glycerol triphosphate dehydrogenase using fat as coenzyme, not NAD as coenzyme. Therefore, there will be loss in energy when the hydrogen is transported by glycerol triphosphate. Okay. This is the mechanism. Now, electron transport chain. Electron transport chain. From the name of these complexes, we now understand that all reactions in electron transport chain, it is oxidation reduction reactions. So electron is transported. So transportation of electron from one compound to another compound, it is a reduction. So all of them are oxidation reduction reactions. Okay, oxidation reduction reactions. This is the outer mitochondrial membrane. This is the inner mitochondrial membrane. Inner mitochondrial membrane. Okay. Outer mitochondrial membrane, it is permeable membrane. Lots of compounds can cross the outer mitochondrial membrane. But the inner mitochondrial membrane, fewer compounds can penetrate the outer inner mitochondrial membrane. It is aspartate, it is malate, it's glutamate, it is hydrogen, electrons, it is malate. So malate, alpha ketoglutarate,
Aspartate.
glutamate, aspartate, and citrate. Few compounds ينعدون على الأصابع اللي هي can across the mitochondrial membrane. Okay. Okay. ATP, ADP also can cross also, but by mechanism. Okay. The electron transport chain. Electron transport chain. Discovered by Peter Mitchell. And Nobel Prize for better lecture. Why? Because he explained how energy produced in our biology. Most of the energy produced by powerhouse organism. It is mitochondria. How? By oxidation reduction reactions and electron transport chains. Electron transport chain. Electron transport chain consisting from complex 1, so embedded in inner mitochondrial membrane. Complex 1, complex 2, complex 3, complex 4, and complex 5. In complex 5, there is no oxidation reduction reaction. It is just phosphorylation. Complex number 1, 2, 3, it's oxidation reduction reaction. Therefore, complex number 1 to 4 with complex number 5, we called it oxidative phosphorylation. So, oxidative phosphorylation. So, phosphorylation only in this complex A, T, B, synthase complex. So no oxidation reduction reaction, but only phosphorylation. Oxidation reduction reaction is oxidative from complex number 1, 2, 3, and this is complex number 5. Okay. Complex number 1. There is another name for complex number 1. It is NAD H coenzyme Q dehydrogenase. Okay, so complex 1, NADH coenzyme Q dehydrogenase or NADH dehydrogenase enzyme. So it is complex enzyme consisting from many proteins. So enzyme and FMN FES. What is the FES? FES, it is the non-heme iron protein. And a protein consisting from iron, but it is not in form of heme. Heme, it is tetrabirol ring. Yes? Tetrabirol ring. And center, it is center, tetrabirol. Between them there is iron. This is heme. But iron, non-heme, it is FES. S is sulfur, Fe iron. So protein consisting from iron and sulfur. Okay. What is the coenzyme Q? Coenzyme Q is a lipid. Coenzyme Q is a lipid. And it is soluble in lipid. So cannot move. Can move. It is soluble lipid. So can move between complexes and can accept 2 electrons and or 1 electron. So can accept 2 electrons and can accept only 1 electron. When accept 2 electron, quinol, all except all reduced to alcohol, can donate 1 electron, semiquinone, can donate 2 electrons, become quinone. So only 1 electron can donate. صار يعطي هذه نول تعطي 1 electron to semiquinone donate 1 electron, become oxidized, loss of electron, quinone. صار هذا كان يستطيع أن يكتسب 2 electrons plus 2 electrons become quinol. quinol أو أحيانا نسميه فيه coenzyme Q82. So electron is transported to coenzyme Q as a hydrogen. So can accept 1 electron or can accept 2 electrons. Can donate 1 electron or can donate 2 electrons. Okay. NAD is coenzyme Q. Okay. Complex number 2, it is a complex which involved in the Krebs cycle. In the Krebs cycle, so this complex, it is complex in which the succinate by Krebs cycle converted to fumarate and the fat reduced to fat 82. Therefore, we call it succinate dehydrogenase complex, another name. Succinate dehydrogenase complex. Succinate dehydrogenase complex. Or succinate coenzyme Q dehydrogenase. Okay. So consisting from also FES. And FES, lots of FES. It is not only one protein, FES, and different FES. Some FES consisting from 5 FES, 5 molecules of iron, 2 molecules of iron, 3 molecules of, so lots of FES in complex number 1 and complex number 2. Okay, complex number 3 is cytochrome reductase. Cytochrome reductase enzyme complex. cytochrome reductase complex أحيانا يسموه فيه cytochrome dehydrogenase complex. Cytochrome dehydrogenase complex. Okay. Complex number 4, it is cytochrome oxidase complex. Cytochrome oxidase complex. Cytochrome